Okay, friends, let's just take a quick video here to make sure we see the differences and the similarities in the two types of arithmetic averages we've seen. We've looked at a raw data average and a weighted average, and both of them do the same thing. I want to make sure that we see why they are indeed doing the same thing. A raw data average is pretty straightforward. All you do is you have a bunch of data, you add up all the values of that data, and then divide by how many there are. It's the average you've probably been doing since you were knee-high to a grasshopper. That's a raw data average. A grouped data or weighted average is different. You're given your data in some kind of a table or a chart. You can also do these from charts, which is actually pretty cool. And then there's a small process. The first thing is you multiply each data point by its frequency of occurrence. Then you add up all of those things you just multiplied and then divide by how many there are. Now, as different as both of these kind of definitions are, it's actually the same math, just done in a different way. Let's take a look. Let's suppose we have this data right here. I just made up a data set just to discuss. Okay, so a raw data average, the kind you've been doing forever, you'd add them all up and then divide by how many there are. So if you add them all up, you get 53. There are 12 in the list. You divide and you get 4.4. Okay, if I give you that same data in grouped form, here's what it looks like. Same exact data. There are 4 2s. 1, 2, 3, 4. There are 2 3s. 1, 2. There are 2 8s. 1, 2. You know, again, I'm just keeping track of how many there are. Sure, there's only 1 6 and 1 7, but that means it has a frequency of 1. I take that table, I take each frequency and multiply it by its corresponding data value. I tried to keep the colors consistent from the last video. That would look like this. So it's 2 times 4, 3 times 2, 5 times 2, and so forth all the way across. And then I'd add up the frequencies because that's how many total data points I have. 4 2s, 2 3s, 2 5s, and so forth. That means I have 12 data points altogether. If I do the math, it comes up with the exact same thing because they are the exact same thing. It doesn't matter how you do the average. This is just a slightly more efficient way of doing it with certain data sets. I'm not saying it's the best for all data sets. It's definitely not. But that's all a weighted average is. It's another way of looking at a data set's average. Okay, so that's the two kinds of averages. We're going to focus mostly on weighted averages in the next series of videos. What I'm going to do in the remainder of this video is I want to chase down something that may have bothered you from the last video. A lot of students, when we get done that experiment that we just did in the last video, they don't like the average of 2.5 flips per trial. They say you can't flip a coin 2.5 times. You either flip it twice or you flip it 3 times. You can't flip it 2.5 times. Never said you did. We said the average was 2.5 flips per trial. Just like the average number of kids in America used to be 2.5 kids per family. Nobody has 2.5 kids. Some have 2, some have 3, some have 1, some have 4, some have 5, some have none. But the average was 2.5, just like the average number of flips is 2.5 here. So in these last few minutes of the video, I'm going to go dive deeper into that 2.5. If you're not interested, you can stop now and go to the next video. But those of you that are interested in seeing like a deeper dive, let's take a look. Okay, the first coin of our experiment either came up heads or it came up tails. That's a given. Now, half the time, it's going to come up heads, and half the time, it's going to come up tails. That's a mathematical, probabilistic, random fact. We don't know which one's going to come up each time, but half the time, over the long period of time, you're going to get heads, and half the time, you're going to get tails. Okay, the experiment has to go at least 2 trials. Let's go out that next trial. Again, you either get heads or tails, depending on what you got the first time. And it's random. It's random. That's why all of these also happen 50% of the time. Now, some of you might be a little bit confused because if you add 50 plus 50 together, you get 100%. And if you add all these 50s together, you get 200%. But you have to realize what a tree diagram is showing you. You start here, and then you trace down the branch to figure out the total probability. So for example, if you got heads first and heads second, what is the chance of that happening after 2 flips of a coin? Well, if half the time you get heads after half the time getting heads in the first place, stands to reason that should be 25%. Half of a half is a quarter, 25% of the time. Similarly, half of the time you get heads and half of the time following that you get tails, you should also have a 25% chance of going heads then tails. You should also have a 25% chance of going tails then heads, and also a 25% chance of going tails then tails. Please notice these add up to 100%. And that should make sense. If we don't look at just the piece, which is the half that is heads here, but also trace it all the way back to the beginning. And that's what you have to do. Go all the way back to the beginning and chase a branch all the way out. Now at this point, I want you to think about it. This point, 2 of these branches, according to our experiment, we're done. We're done in this top branch because we got a repeated head. We're also done in this bottom branch because we got a repeated tail, which means 25% of the time we're going to go heads, heads and be done. Also, 25% of the time we're going to go tails, tails and be done, which means that 50% of the time we're done after 2 flips. But how about this 50% here in the middle? Well, they have to keep flipping now, don't they? Because we haven't gotten our repeat yet. We know we're going to get a repeat on the next flip. Let's take a look at it. Now here, what I did here was I wrote in the fictitious heads or tails off of the top and bottom branches because in our experiment, they don't exist. But when you flip 3 coins, they do. It is possible, for example, to flip a coin 3 times and get 3 heads. It just wouldn't have happened in our experiment. I'm more interested in chasing down these probabilities here. Now we know already that these 2 outcomes add up to 50%. These should as well. Let's chase them down. Okay, going back to the beginning, half the time we get heads, half the time after that we get tails. So at this point, it's at 25% or 1 in 4. Starting at 1 in 4, half the time after that, we're going to get heads. Well, half of a quarter is 12.5%. The same 12.5% that would occur here, the same 12.5 here, and the same 12.5 here. And if you look at all of that, they add up to 50% of the time. So half the time we were done back here in the second coin, and half the time it's going to take the third coin. So if half the time it takes 2 and half the time it takes 3, it stands to logic that the average should be directly in the middle. And there's another way of looking at why the average number of flips to get a repeat is 2.5. I hope that helped. Let's go on. Let's make a new experiment now. I think you're all getting tired of this flipping a coin till repeat. Let's make it more interesting. All right.